Good morning. This is a design project for SES 141, and I understand that I'm taking the only artistic thing here is the artistic license that I'm taking in referring to this as a design project. But I wanted to take advantage of the class and the sharing of information on how to estimate in that class as a project in an area that I'm very much interested in, and it has to do with Drake's equation. So let me explain a little bit about what I want to do this morning. I want to talk about specifically about Drake's equation, and in specific terms of the efforts within the course, there are three estimates that I want to work with, and I'll explain more about why those are in my range here and today, just a little bit later, and explain to you what is the real factor in Drake's equation that I really want to look at that's important to me. So Drake's equation is really about reaching out to ET, and that's why I had the little picture of ET on the cover of this deck. Drake's equation is not really so much of a formula as a framework for looking at the universe and what we know about the universe at this point in the world, and what the likelihood is that we will be able to find life, intelligent life, and life that we can communicate with, and what's the chance of us actually running into people who are at least as advanced as we are. And that has something to do with the factor I want to look at, which in this equation is the last term that you see there. That's the capital L. So the factor of interest to me is L, the length of years that a technologically advanced civilization remains viable. Obviously, the length of that civilization stays around and is able to communicate and has technology has a lot to do with whether or not we can bump into them, because the universe has been around for about 13, 14 billion years. That looks like a long time, and we think that maybe there's a lot of life out there somewhere, but the chances of us actually running into life are very much dependent on that L factor. If a typical civilization in the universe gets to the point that we are today, but only stays there for a few years relatively, then our chances of running into them, the chances of our little piece of time that we have as a viable species and a viable civilization may not be in sync with when their piece of time is around. So not sure where the research is for this, but scientists have published an estimate to say that they believe that we have about 200 years as a viable civilization here on Earth. And like many other of the other factors that are in the Drake equation, they lean heavily on our own experience. So for a long time, of course, we were looking for carbon-based life because the Earth here is carbon-based. And they began to look a little broader than that eventually. But at this point, as far as viable civilizations, we only have one to look at as a model. We can't really project anything beyond that. And they're saying we have about 200 years, and therefore the L factor in Drake's equation should be about 200 years. So to refine this, or to maybe better understand this, can we approach this estimate of the L factor through techniques that have been learned in S141? This is a great question to exercise the techniques that we have learned in SES 141, I believe, because L is based upon best guesses, and anyone's guess is as good as another, so long as at least it is logically produced. Now, so when we're thinking about that length of time that we are existing as a civilization, typically People talk about the reason that a civilization might end, at least our civilization, for example, would be massive nuclear war that completely wipes out the species. Or there could be another event like the one 66 million years ago that wiped out the dinosaurs that could wipe us out as well. But not assuming anything of that dramatic nature, I'm more prepared and looking at and interested in looking at, given the situation as it exists today, what we know about the situation with our species and with our civilization today, let's look at the things that really are keeping that civilization alive on the one hand, and also threatening its existence on the other. And one of those is fossil fuels. We can't do much without fossil fuels, but there is a possibility that we could run out of fossil fuels. So is that something that could cause the collapse of civilization? There's overpopulation at a global scale. Even today, could effects related to overpopulation cause a collapse? And of course, there's probably the most imminent threat that we are aware of is climate change and what the effects are there that could result in civilization collapse. My contention that we need to look at all three of these in a trio because they, in my view, are very much interrelated. So starting off with fossil fuel depletion, and I'm just going to take a swag, but it's based off of, my swag is based off of something that we are currently observing. Some of the countries in the Middle East are already preparing to get out of the petroleum business. They want to build economies that are based on other means of creating a lifestyle. So given that they're very uneasy about the longevity of fossil fuels as a viable means of keeping things going, I'm going to say, based off of their pessimism, that maybe we don't have more than 100 years. So that's going to be my first guess. We've got 100 years to keep things going and to potentially meet somebody outside of our planet. The second technique that I want to apply against that guess is use what we know. The energy spiral, the tool that we've been using in SES 141, gives the energy content of a gallon of gas as 10 to the 8th joules. At the same time, the energy spiral shows that the total fossil fuel reserves on Earth contain about 10 to the 24th joules of energy. Other things that we know, there are 8 billion people on Earth. I'm going to guess that maybe a quarter of them are gasoline consumers on a daily basis, and that they consume at least a gallon of gas to get back and forth to work every day. That's about somewhere between 30 and 50 miles. So there's 2 billion of them consuming a gallon of gas every day. And on top of that, I'm going to assume, take a guess, that industry also consumes the same amount of energy each day that those 2 billion people above have consumed. So we know that there's a lot of energy in the fuel reserves, but I'm assuming that only about half of that can be found and retrieved. That's simply because things can lie around in very strange places, deep under the oceans and areas where we haven't been able to get to before, and in other locations maybe that we just haven't been able to locate the resource, or maybe it's just too difficult to get it out. Fracking, of course, came along a few years ago and managed to create a new thread or new stream of fossil fuel, but we can't count on that constantly. So if we assume that we can get out half of it out, then that's a half of the 10 to the 24th, or that's 5 times 10 to the 23rd joules that we have available to us somewhere underneath the ground. So if we take the total amount of energy that we've got available to us on Earth in fossil fuels, of course, that's that stipulation, and we divide that by what we're consuming every day. So that's 2 billion people. That's 2 times 10 to the ninth, and times 10 to the eighth joules that we're consuming by those 2 billion people every day. And then we multiply that times 2 again, because we're including an equal consumption by business. That works out to, if you do the math, of 10 to the 6 days. And 10 to the 6 days is about 2,500 years. So technique 2 is quite a bit different than technique 1. We're separated by 2,400 years. But this technique 2 is based off of information that is real and would give us a comfortable feeling that we're going to have fossil fuel around for a while. Obviously, we're looking into other sources of energy, but it's my contention that in the foreseeable future that we're probably going to be heavily reliant upon fossil fuels for our energy sources. So since we got 2 answers in the first 2 tries that are pretty far apart, I'm going to say let's use another technique. Let's split the difference. So halfway between the first and the second estimates gives us a new estimate of about 10 to the third years. So this gives us some hope that maybe those scientists that said that it was 200 years only were a bit on the low side, a bit pessimistic, but they're not grossly low. We're still, in the 10 to the 2, 10 to the 3 range of time left for keeping the civilization alive, at least with fossil fuel. However, the other 2 factors that I talked about earlier, population growth, also come into play, even when we are just looking at fossil fuel use. So let's have a look. Overpopulation in population. When I was born 75 years ago, believe it or not, I was around that long, the global population was 2.5 billion. Today, the global population is about 7.5 billion. Now, some folks round it up and say that's 8. I'm going to keep it at 7.5 because it keeps my math a little bit easier. The midpoint between these 2 numbers was reached in 1986 when I was 40. So the upward trend is still increasing, but at faster rates. So it was 40 years to get from 2.5 to 5. It's only been 35 years to get from 5 to 7.5. So that means that I'm projecting and keeping to that same curve, that in about 30 years, we should be at 9 billion. Then the 25 years after that point, all the way up to 11.5 billion. And then 20 more years would be up to 14 billion. So around 2100, I'm expecting that we'll be around 15 billion. And I think there are other projections that have also, over the last part of the century, estimated that we would get up to about 15 billion. So what happens if we get up to 15 billion by the year 2100? What happens to our petroleum supply? Well, suddenly, of course, it's not over the entire time, but the projected lifetime then at that point of our supply would have backed down from the 1,000 years that we had agreed to earlier down to probably 500 years. So we've halved our petroleum life expectation simply because we've got a lot more people on the planet. In addition, of course, this will also, that is population growth, overpopulation, is going to have some pressure on climate change. So we'll talk about that a bit. So climate. Recent announcements from COP26 are that the global temp is now about 1.25 degrees above pre-industrial levels. Okay, they were all happy about that because they were afraid that we were already at 2. Because the target for avoiding climate ruin and getting into some kind of perpetual motion machine, as far as the climate is concerned, in heading toward disaster, is about 2 degrees above pre-industrial levels. That's not the climate ruin itself, but that sort of sets the mechanisms in motion in order to get you there. So looking at this and knowing that the Industrial Revolution started in the late 18th century, but the adoption of the gasoline engine didn't really come about 100 years ago, expecting then that probably a lot of the increase has come in the last 100 years. So we know that 1.25 currently is already real, maybe a bit smaller than previously thought, but it's still a real thing to deal with. Another element of this, other than just the gasoline engine and other factory uses that have come out of petroleum, is that I believe that when you look at not just what people are doing, but how many there are, that really one of the prime root causes of climate ruin is going to be population growth. Simply so many people on Earth, no matter what you do with them, if they need to consume things, then there are going to be problems with the climate. So using my assumption that the temperature rise really is dependent upon and follows the population curve, we can look at it this way. So 1800 was when all of this started, and it went up in clips until we reached 2020, and now we're at 1.25. Continuing into the future, around 2030, I'm projecting using my little population curve that we get up to around 1.5. By 2035, it'll be up to 1.75, and by 2038, it's going to be approximately 2 degrees, the magic 2 degrees when the mechanics all kick in. This will then bring us to getting up to 3 degrees above pre-industrial levels by around 2050. So why am I pessimistic about us being able to avoid it, that we probably won't be able to avoid that, are these. Every time there's a COP meeting, and we just had our 26th, the countries deliver promises that are all soft. This time, there are a few countries that will implement hard restrictions, but those don't include the big two, the US and China. So I'm convinced that these things will not remediate the climate change that's coming, and that we'll have that 3 degrees rise by 2050. And that will then mean, by the time we reach the end of the century, a 3-meter rise in ocean levels. That's the biggie. A 3-meter rise will mean that we abandon most of Florida, the coastal areas along the Gulf Coast, and the same for much of the East Coast. That means tremendous amounts of migration inland into the continental United States. In addition, for those that are left or those that are able to get to it, increased heat, 3 degrees is going to mean it's hotter everywhere, will increase electricity consumption for air conditioning, which already consumes, as we know from materials that we've seen in the last few weeks, about 20% of electricity production being consumed by air conditioning. So if it gets hotter and hotter and hotter, almost 3 times hotter than it is today, or not 3 more degrees than it is today on average, that 20% could go up very high. So when I'm trying to compute L, I'm considering these things, and I'm looking at them as a perfect storm. Increased energy consumption to overcome the effects of climate change in the latter half of the 21st century could easily cut the world's available petroleum supply back by about half. That brings that 500 years we saw earlier down to 250 years. Now, if running out of fuel doesn't do the civilization in, then mass migrations due to flooding could also start to disrupt civilization and bring about its end. Because we're not just talking about a few people moving around and hanging around at the border and causing mischief. This is about millions and maybe billions of people actually on the move across the planet in order to get away from the problems due to flooding. The third issue is that overpopulation, in addition to the stuff that's happening with the climate, can of itself create starvation epidemics in many areas around the globe. And we're already starting to see little trickles of that. And that push of a larger population will further diminish arable land. And then, of course, it's, that's a double down on that problem. So in that perfect storm, I'm saying the best guess for L is really could be as early as 2100, so that's about 75 years from now, to our 250-year estimate based off of fossil fuels. So when you look at it, then we really are very much in line with the published scientific estimate of around 200 years. So what does this mean for Drake's equation? Well, really what it means is, to me, don't worry about ET. We may find him somewhere out in the universe, but we'll be gone before he arrives here, because the overlap in our L value with any other civilization that exists in the universe, the overlap of their L value, and when it occurs in time, that is in universe time, is just going to be extremely small. The chances of two civilizations being coexistent at the same time in the universe and being able to communicate with and certainly to travel to are just going to be extremely small. Thank you.